figuring out what's going on with the. If I do it like this, we'll fix it. Oh yeah, now we're doing better. Okay. Yeah, I'm just kind of figuring out where to put you and so on. Okay. Face is nice and big. All right. Okay, Ryan's good. All right, I think we're all back, etc. Okay, so welcome to second half of the morning session, folks. I'm super pleased to have Tomas with us. Tomas is had the pleasure of being lead TA the first year we ran this, or whatever. Did a great job and so on. Now he's old and established as a postdoc at Caltech. He leads a lot of the sort of follow-up that we do with ZTF, expert in GRBs, kilonova, etc. And so I asked him to sort of talk about how we sort of run our follow-up program. There's going to be some overlap with a bit what Igor talked about, not in a bad way, but sort of, I think it's good to get some of this from a different perspective. And yeah, otherwise, super happy to have you, Tomas.
Thank you, Michael. Yeah, so I'm very happy to be here. As Michael mentioned, I was over Zoom actually on 2021. Just a little about me. I am Tomas. I'm originally from Chile. I did my undergrad at the Universidad Católica in Santiago. Then I moved to the University of Maryland where I got my PhD, working with Leo Singer and Brad Senko and people from ZTF doing multi-messenger astronomy. So I'm going to talk to you, and now I'm a postdoc at Caltech. It started last year. And I will try to be a little bit more low level for people that haven't really heard of multi-messenger astronomy generally. So hopefully you don't find this too basic. So just going to mention first what we refer as messengers. So we receive information, right, from different, what I like to think as particles, right? There are a bunch of different messengers in that we have used across history, but the basic one is light. So we receive information through photons, and these photons would then, thanks to Newton and people like that, they discover that, you know, they have different wavelengths, and you can derive different information from different wavelengths. So here's a little scheme of what humans have basically derived. You have wavelengths that go from the radio to gamma ray, from less energetic to very, very energetic. And here is basically the atmosphere. You have a bunch of heights at 10 kilometers, 100 kilometers, and 1,000 kilometers. It's where we can basically see stuff. Our atmosphere is transparent to optical, and that's why we see in optical, but also is somehow transparent to radio. And it's not because of some gases that are in the atmosphere transparent to infrared, for example, or ultraviolet X-rays and gamma rays. So whenever we want to observe this stuff, we're going to have to put the detector on a different, a less conventional telescope. So for example, there's a plane that was working until last year. It's called Sophia. In the plane, there was half the plane was a telescope, and they were looking for infrared stuff. There's another, there's now a bunch of infrared detectors that are out in space. Ultraviolet doesn't penetrate the atmosphere, so we have to put things out in space to see stuff. Sometimes people would just fly a balloon with a detector. Sometimes we'll just send a rocket, but this is basically what we have been used for centuries. Other messengers that you have heard already from Robert yesterday are neutrinos. So I'm just going to say that they exist because I actually don't know really much about them. Cosmic rays are another sort of messenger. So in this, I put these two together because in my head, these are much more tangible particles. So what happens with a cosmic ray is whenever you have a very high energy particle that collides with our atmosphere, it creates this chain reaction that you can see here, like a pion creates a bunch of energy basically, and you can detect that energy if you have the correct instrumentation, and then you can basically derive what it comes from. And that's what people have been doing for these sort of cosmic rays. And the last one, and more exciting, at least for me, it's gravitational waves. Gravitational waves, I guess, they have been mentioned, and just wanted to say again that it occurs when very massive objects are moving basically very fast. So you have what humanity has made, we call it the LIGO interferometer. It's basically a laser that is shoot back and forth to a mirror, basically two mirrors, and you can measure the difference when a gravitational wave passes through this area. I put also what we have observed, and if you think about it, we just not really observe as we used to with our eyes. It's basically we are detecting the movement of space-time, and on blue here and orange are the objects that LIGO have observed, and in purple and in yellow you have the things that have been observed with photons. So if you see here, for example, above 20 solar, this is solar masses. So you have neutron stars that are a little bit heavier than a solar mass, and then you have black holes that have been observed from electromagnetic observations, basically X-rays, that lay between 5 and 20 solar masses. But then with LIGO, we have very, very much opened an entire new sort of like window into how to study these black holes. So you have 20, 30 solar masses objects that sometimes merge into 160 solar mass object. So putting this together, basically, it's what Multimessenger is about. We are trying to do joint detections between different sort of messengers. So I'm gonna just show you what have happened in the past. You have what the first sort of situation happened in the 60s. So neutrinos were predicted kind of like a century ago, and people have been obsessed with them. So the idea was, there's this very mysterious particle that we could have detected, and how can we detect? So there's notes from Mr. Davis, I think it's Robert. He got the Nobel Prize after, Raymond, sorry. He got the Nobel Prize after actually building a neutrino detector and getting evidence from solar fusion. So basically they're trying to use if it interacts with the particle, would sort of create a recoil in the nuclei, and then you can measure that because there's a set amount of energy that you can detect. This is a picture from, I guess, the 50s, where they were working in in a coal mine in South Dakota to build this detector, because it has to be very, hidden and protected from other particles. And this is Kamiokande. This is a detector in Japan that detected the supernova, the neutrinos from the supernova that happened in 1997. And this is how it looks. It's just like a bunch of detectors around, it's surrounding this like sort of like wall, I guess. It's also very hidden and protected, but this is basically the trace. So I guess Robert showed you yesterday a very evolved version of this same plot. So basically we're tracking here time, and here you're tracking the position, and then you have basically the trace of the neutrinos that we're going through in this detector. So these two people got the Nobel Prize in 2002 for this joint detection of in this case, light from the supernova and the neutrinos. Actually, neutrinos came first, and then 2 hours later, people were like, oh, there's a supernova. There is ongoing an effort to correlate the cosmic ray background, the gamma ray, high energy gamma ray background, and the neutrino background, because people think that they're somehow related. So you can see this is basically the Milky Way, and then you have this is the neutrino, those observed neutrinos in these galactic coordinates. And here are the high energy cosmic rays. So the idea here is that people have found evidence, and there was a paper on a neutrino paper not long ago talking about this. So again, trying to put everything, a joined multi-messenger astronomy. And the one that I like the most is basically, well, 17 you probably have seen this 1,000 times already, because I know Igor showed it 1,000 times. So even if you didn't know about it, Igor made sure that you have this neutron star merger, and then you have this beautiful, I'm just gonna put it again because it's so pretty. So you have the collision, and then you have what we call the gamma ray burst, and then it's interacting with the environment. So you have an afterglow, but then what is left over here, it's the material that is undergoing nucleosynthesis, and it's also powering what we call a kilonova. So that's basically one of the most famous multi-messenger detections from the gravitational wave side and the electromagnetic side. I'm just going to focus now on 17 just to give you a brief context. And this is a localization map. I guess it might be a little hard to sometimes understand. So this is a projection of the sky. So you have the coordinates of the sky, and whatever shaded regions are the higher probability locations for where to find the binary neutron star merger. So in this case, you have a lot of you have 3 different detectors. So you have LIGO, which is looking into gravitational waves. Then you have gamma ray burst, gamma ray instruments. So you have Fermi. This is the region that Fermi observed. And then there is the interplanetary network, that it's basically triangulating different signals from gamma rays. And this is the region that the interplanetary network derived. So when you put everything together, you have a much smaller area. It's only over here. And when you look into the galaxies that were there, you have this particular galaxy, 4993, NGC 4993. And then if you compare these 2 images, this was taken 20 days before, this was taken 10 hours after the merger. You see that little thingy that was not there, that little dot. And it's kind of like, it's different to what we have artistically thought. The video that I showed you is just like an artistic impression of what happened over there, but what actually you're looking for, it's basically a dot. You're looking for something that was not there before. And when you look into the evolution of it, so this is what we call a light curve. I'm sure that you have already seen this from yesterday. You see that particularly this object evolved from magnitude 17th to magnitude 22nd in 4 days. So it's one of the fastest evolving transits that we have seen in history. So that caught the attention of basically the entire world, and it's basically the most observed transit that has been ever recorded. Here you have on the right the gravitational wave time frequency map on the bottom. So you're looking here at the frequency of how fast these things are spinning versus the time of trigger. So you're expecting that it basically goes to a higher frequency as it approaches merger. So you see it's going up, and then eventually it merges. And 2 seconds after, you see a gamma ray burst. This is the Fermi light curve, and this is the integral light curve from out of space, basically. And you see that these are both consistent. You see a spike. This is what we call a gamma ray burst. Why is it important to study these objects? Well, generally you can study and like get a lot of information from just one messenger, but when you combine them, you can basically exponentially increase the amount of knowledge from this object. So in this case, we thought for a long time that these were sites for nucleosynthesis of very heavy elements. So I'm sure that people have seen the periodic table, and the ones that are very heavy, the ones that are very massive, we think that that's where they're created. And naturally, this is a place where their jets are created, and we can study the jets if we know where to look for. We can study what is left, so that's what we call a remnant. It's natural particle accelerator, and you can see from basically radio to gamma rays, and you can have a very comprehensive study of these events. So this compact binary merger has caught my attention, and you can study it from different angles. So my PhD was based on the search for short gamma ray burst in this scenario. But I'm also going to talk about gravitational waves. So just to introduce you, for people that haven't really heard of what a gamma ray burst is just this. It's basically the most energetic explosion that we have in space. It was discovered in the 70s. It's one of those things that we never really knew. So in the 70s, people knew that fission would produce gamma radiation. So they send military satellites to monitor nuclear activity on Earth. But they started discovering that there were other things. They were detecting other things. And eventually they figured that they were not coming from Earth. They were coming from out of space. So this is the compilation of bursts that happened. So this is in the 70s. So 30 years after, you have a number of these events, and you can see here that if you put them and sort of group them by duration, this is what we call T90. That's the duration of the burst. You see that there's basically a bimodal distribution. So some of them will peak around here, and some of them will peak around here. And that's what people were, at that point, it was like, okay, if there are two peaks, there are probably two different populations, right? So they feed a Gaussian here, they feed another Gaussian here, and then they said, okay, we are going to separate them in these 2 seconds. So whatever lasts less than 2 seconds, we call it a short GRB, and whatever lasts for longer than 2 seconds, we call it a long GRB. The physics of how do you produce this GRB is still very, it's unknown. So I invite you to solve that mystery for us. But there are ideas, right? So what they have in common is that they have, they sort of require, to produce this amount of energy, they require a hyper-accreting black hole or a rapidly rotating neutron star. And you have a lot of ways to produce that. So for example, if you have two neutron stars that merge, one of them, the tidally will get disrupted, and eventually when they merge, they will create a black hole. So then you have a hyper-accreting black hole, and then you can sort of fuel these very, very fast jets. You can do the same if you have a black hole and a neutron star. You can do the same if you have a black hole and a white dwarf. So basically, whatever has a black hole that kind of accretes material from a compact object. Sometimes, and this is has been proved like not too long ago, you can have a black hole or a neutron star that goes into the envelope of sort of like a star. So they were two stars evolving, and then the envelope of the puffier one sort of like absorbs these two. So you have material around, and then you have the merger inside sort of this envelope. Or you have, and this is the last sort of scenario, what we call a collapsar. It's a collapsing massive star. This happens when you a very massive star that undergoes the collapse of the nucleus, so it's basically a supernova. It's dying, but it's so massive that it basically sort of like fails to explode and like push everything out, and some of it will fall back to the accretion disk of this newly created black hole, and that will probably fuel the jet. So whatever it is that creates a gamma ray burst, you have multiple types of progenitors that could do this. This jet will push through and interact with the material that's surrounding the star or the event, and that's what we call the afterglow. So this is basically synchrotron emission that it's visible from the radio to the X-rays, and that it's very particular to these sort of jets. Depending on how fast it is, we measure that using this Lorentz factor. The higher the Lorentz factor, the more like the faster it goes, and the more energy you can put into the system. But that also relates to how long it lasts and how bright it is. Eventually, this jet will lose energy because it's sort of like depositing into the system, into the environment, right? And that's what we call a jet break, because it's losing its energy. So it's less, it's just less bright. Eventually, as you see here in this like sort of caricature, you see that how the jet spreads to the sides as it loses its energy. It was originally very beamed because of how energetic it was, but then it's sort of like it's spreading, and you can see that in the light curve. So you see a jet that is going down, a transient that is going down. This is magnitude. This is how bright it is versus days. So this is a light curve. Oops. And it goes down very fast, and then eventually goes down faster because you sort of like broke the jet. You can also see it from the outside. So sometimes you have a very narrow jet, and you might not be in the center of the jet, so you're not going to be able to see at the very beginning. But eventually, as the jet spreads out, you can start seeing more and more of this energy. So this is the black line here. It's when you are on the center of the jet. But if you're sort of like in the outsides, you will start seeing something that rises sort of like slowly and then fast and decays very fast. And similar if you're like farther away. So to put this together, people thought originally that this bimodal distribution was directed to two different populations, right? So they started studying and that they associated compact binary mergers to short GRBs because they are just smaller, and then core collapse supernovae to longer GRBs because basically they're more massive. You have more time and more material to accrete, and then it's easier for them to create a longer GRB, a longer gamma ray emission. But these are two very small objects, so you might expect to it's sort of like a boom. Just a reminder, long GRBs are massive stars. So since they're very massive, it's really hard when they explode that they put everything outside. And since they're usually rotating, stars just rotate like the sun rotates. This sort of movement will make the gas twin spiral instead of just falling back into the black hole, and that creates the accretion disk, and that fuels the long GRB. Here is a light curve of one of the supernovae that is associated with this long GRBs, and I just put this to see that okay, you pick here, let's say at day 20, but you keep fading over hundreds of days, which is very different from what you would expect from a kilonova. A kilonova peaks within a few days and then fades very quickly to levels that we cannot see after like a week, depending on how far it is, basically. But supernovae will be there for half a year, maybe sometimes even more, depending on how close it is. And it's the same. It looks very similar. It's just a dot. It's just a blob in this like sky picture, sky image here. Which is very different from, again, like a kilonova. And this comes from what is fueling the transient. In this case, kilonova are fueled by our process nucleosynthesis. So the decay of these very heavy elements will create this sort of very red fast transient. I'm sure that you have seen this. So again, you have in the central engine, basically, in this case, a black hole, you have an inner sort of accretion disk, but then you have the tidal ejecta and more ejecta from this merger, and this is what creates the kilonova. In the center, you have the jet that it's here. So you have the GRB prompt emission, and here's the interaction sort of with the interstellar medium that creates the afterglow. And then you have some other interactions that, in this case, it's a cocoon that that it's surrounding the sort of the jet, and this is the shock breakout. So it's very complicated because there's like a bunch of things, and it really depends on where you're looking into this sort of objects. So short GRBs, depending on, again, you are located. If you are basically on the barrel of the jet, you will see the gamma ray emission, but you won't really see it unless you are in the jet barrel. So if you're going out of axis, basically, if you're looking from here, you will miss sort of the GRB, but you might be able to see the afterglow. And eventually, if not, you will definitely see, well, you could see the kilonova. And that's what Igor has been trying to find using ZTF. What is the basically probability to just find a kilonova if we are looking off axis? And it has been proven to be very, very hard because the fast fading nature of the kilonova, but also the distances and the ZTF limits. There are people that are just looking for afterglows that are not related to a GRB, like Anna Ho, which has a bunch of papers about this. And there's me that is just looking for short GRB counterparts. So just as a summary, you have either a long GRB or a short GRB. This is the canonical classification because over the past year, this is this has been questioned. You have long GRBs, you have short GRBs, depending on the duration. These both are powering this ultra relativistic jet. That's what we call the prompt emission. And that jet is what powers the afterglow, which is coming from synchrotron radiation, and it depends on the angle. These two green things are common to both of them. So it's really hard to distinguish what is the progenitor from just the afterglow. You don't know if it's a merger, you don't know if it's a collapsing star or something in between, a white dwarf or neutrons are in a black hole, or the neutrons are going into the envelope of a more massive star. What will tell you it's sort of the aftermath. So if you observe a supernova, if you observe radiation that's long lasting and has, elements that are created in the supernova, you can confidently say that it's a collapser. And on the other side, if you see a kilonova, which is much faster and much redder, you can say, you can associate it to a compact binary merger. And this is where the gravitational wave sort of link comes. So you have light, you observe light, but then you want to link it with this new sort of like messenger, which is the gravitational waves. And that happened once in 2017, and we're all very much waiting for the second one. So in practice, it sounds easy. At least for my thesis, it was like, okay, Tomas, just go find short GRB counterparts using ZTF. But that was very hard. So it sounded easy at the beginning. And I was like, okay, I'll just use ZTF and look for counterparts. You already played with some of the ZTF data, some of the alerts, and it's quite it's quite the job. So I try to find these compact binary merger using the short GRVs, and we are looking for short GRVs that are detected by Fermi. So this is the Fermi satellite. In the Fermi satellite, there are two instruments. There's the Large Area Telescope that is over here, and this was made to detect very, very high energy gamma radiation. But also there is this gamma ray burst monitor. So there are a bunch of these, like, you can see sort of like a silver circle here and silver circle there. And these are the detectors. This is the GBM, gamma ray burst monitor. And it's basically every detector, it's like a telescope that it's looking into just one direction. So if a gamma ray comes this way, it's detected by this sort of detector, but it's not detected by the one that it's looking the other side, then you can say, oh, the gamma ray was in this direction, but not this one. So that's what basically GBM is doing. Why are we using GBM? There are a bunch of other gamma ray telescopes. There are actually some of them that will give you a very precise measurement. But the issue here, well, the good thing is that GBM was actually the one that detected 17 or 17. So we know that it will detect gamma ray bursts from compact binary mergers. It is very sensitive. It detects much more. It detects more GRVs per year, and it's because it's looking to the entire sky. So it's a very good instrument, but the only challenge is that it has very poor localizations. But that is not really a problem for ZTF. So here I'm showing, this is the first GRV that we trigger in 2018 now. This is a paper that Michael led. So you have, this is a projection of the sky again, and the red area shows the higher probability. You have the probability from 1 to 100, right? With 100%. And you're dividing this probability in this sky map. And you're saying that here you have, I don't know, 20% probability. And we are here putting in circles the 50th level. So you have 50% probability of finding it if you look into this area. And here's the 90% probability region. So the 90% in this case was basically a quarter of the sky. So you have to look into a quarter of the sky to find just one event, in this case, that was the afterglow or the kilonova. How did we do that? We used the Zwicky transient facility. You've heard of it before. It's a 47 square degrees, so it's a beautifully large field of view instrument. What it really is important is that it's survey anyways. We don't really have to. Will happen, and the ZTF will look into the sky every night. That is possible, basically. And that allows us to see things that were there before and that we're not interested in. So this is what you guys did yesterday. You took a bunch of sources, and then you went through a filter to reduce the number of alerts that were interesting to you. So this is what we have been doing for a long time. We take a bunch of sources. In this case, we started with 170,000 sources. So that was a lot of sources, but we ended up with maybe a couple dozens. And that's only because we were looking into the previous history. We looked into the light curve of the data. Sometimes you find, supernovae that were just there before and we're not interested in them. You can look into the color evolution because we know how kilonova evolve in time. We can look into the magnitude evolution of those. So not just the color is the difference between two filters. So how red is compared to or how blue is compared to other wavelengths. And the magnitude is just seeing how much brighter or fainter it gets in just one filter. We have a bunch of checks. One of them corresponds to checking whether AGNs are in the area, or and eventually, if you're looking for more in-depth candidates, you can look for hosts. So kilonova are intrinsically fainter than supernovae, for example, or afterglows. So if you have a host visible, it might indicate that it's closer. So you can probably say that with more confidence that it might be associated with a kilonova. But eventually, you get a number of candidates. On average, we did this like a bunch of times. We did like 10 follow-ups, and for every follow-up, we basically had to be very thorough and either look for the photometric evolution. So in this case, you have this this transient. So we look for the evolution. In this case, it was rising, and it took like 60 days to rise. So it's like very, very uninteresting. Or you can look into the spectrum. So we know what is the composition, for example, of a supernova, and we know the composition that we expect from a kilonova. And you can compare these compositions. So if you find, for example, hydrogen in one of these spectrum, that it's likely not kilonovas. So you can just think, okay, I don't care about this one. So again, we did this like a number of times, and different maps here, different GRVs. We stopped doing the GRV searches during 003, during the LIGO 03, because we were drowning in gravitational wave alerts. But we continued after that, and we actually found something super interesting. So we discovered we discovered the shortest gamma ray burst coming from one of these collapses. I'm going to talk about this a little bit in more depth. So here's another version. Here is, let me introduce you, people, GRV 200826A, GRV 200826A, people. GRVs and similarly to gravitational waves are named by the date. So this happened in 2020, the month of July, August, yes, the 26th of the month, and the letter A means that it was the first. It was the first of that day. Here is the GVM 90% region. 90% localization. So it was a very well localized. Actually, Igor was the one that triggered on this one because I was sleeping. I think it was like midnight or almost midnight in California when this happened. So thanks to Igor, we wouldn't have this with this talk. We triggered GVM. This is the 90% region. This is the 50% region. On light blue, there is Balrog, which is another method that uses GVM to localize bursts. And we tiled ZTF. So each one of these squares is one of the ZTF fields. So we did 1, 2, 3, 4, 5. And all these green dots were they're candidates that we sent out after the first night of observations. So we had a bunch of, I think 13 candidates that were very interesting to us. That was like, okay, this makes sense. This could be the afterglow, but only one of them was. Because this was a well-localized burst, another spacecraft detected it. So you can triangulate the region, the signal, and you can have a much smaller area. So this whole area that was spanning 250 square degrees was reduced to this very small IPN region. It was a few square arc minutes. And this region is basically the most updated using all the information from gamma ray that you can have. So if there is something, it will be in this area. There is another telescope mounted at the Neil Gehrels Swift Observatory, which is out in space, that looks into X-rays. So this is the XRT, the X-ray telescope, and it has this field of view. It's much smaller than ZTF. You can compare here. So one of the pointings here, it will be impossible to follow up every single object that we can detect with ZTF. So XRT observe this region, and as I mentioned before, you expect an afterglow, and the afterglow will be bright in X-rays. Although 170817 was not bright in X-rays up until 10 days after the merger. So sometimes you will have a delay. Sometimes it will be upfront, but you will probably have X-rays. So it's a good idea to just like use the X-ray telescope to look for this stuff. Oops. So in this case, you have these are sources that are bright in X-rays. X-rays are very quiet sky, so sometimes it only takes a few photons to call it a detection. And you can talk to Igor about that as well. He's more experienced on X-rays than I am. But the thing is that there was one source in this IPN region that was bright in X-rays and that we detected, and that was consistent with being a candidate. So we didn't have any detections before. So that was now let me introduce you ZTF 20 whiskey, which is basically the name that ZTF gives. It's awful, but I don't know, it has whiskey. So you have here the detection that happened 4 hours after the trigger. Here you have a bright source, and the reference image, you don't have anything. But when you look into the legacy survey, so you look into other telescopes that have looked into it, you have here that there's a very faint sort of galaxy over there. And that allowed us to, okay, we have a distance, we have a redshift, and with the redshift, we can have a sense of the energy. This is where the things were a little bit more complicated, because we were looking for short GRVs because we wanted to get a merger, we wanted to get a kilonova, so we'd like basically trigger everything we had and use every telescope possible to observe this thing, but nothing really was conclusive in terms of what was the progenitor at the beginning of the trigger. So this is a plot that shows the duration of the bursts versus how energetic they were. I think there's a question. If Suvam, feel free to ask your question.
Yes,
Yeah.
hi,
Yeah,
thank
go
you. Yeah, for the same GRB, this 200826A, it is a short GRB, but it has a associated supernovae.
Yeah, with your
So I remember you in the initial slides, you told that if we find a like counterparts like the supernovae, then we can surely say it's a long GRB. And if we found a counterpart of kilonovae, then we can surely say that it's a short GRB. But I don't think we can surely say, because this is a short GRB and it is a counterpart of supernovae rather than a kilonovae.
yeah, you're stealing my my punchline. But yeah, so that's basically what.
Oh, sorry, I spoiled it. Okay,
That's okay. That's okay. But I will get there. So if anybody has another question, we can probably catch up later.
Okay, because there is one other GRB.
There are two other objects that are now like debating and
yes.
but that's what's interesting, because we have we're challenging basically what people have thought for years, and I'm just showing some evidence that some things are not what we thought. People have thought, people have found other counterexamples on the other side of the long GRVs that look like mergers, and things are just getting more exciting. I think so far we have only 3 confirmed events that sort of like challenge this classification.
So my question, regarding that, my question is that like, is there any other way to like surely say that this counterpart associates to a short GRB or to a long GRB? Because there has been like contradictory observations, right? So
I feel like the issue is the classification. It's not like I don't think, and I will get to there, but as I mentioned, people in the past, in the 50s, and the 70s, they were like, okay, short GRVs, long GRVs, end of the issue. But you clearly see an overlap, and this is where I'm showing in this sort of plot. You have T90, which is the duration of GRV, and if you clearly, this is 1 second, right? So yes. This is 2 seconds, and if you just draw a line here, it will be very hard to say, and it will be very hard to believe that whatever is to the left, whatever is to the right is a collapsar or a merger. And I think the association between duration and progenitor is what it's on the question now. So to answer your question, is there any other way to check what is the progenitor? Yes, the way is to find the optical counterpart, which is extremely hard. So
yes.
from just so is that answering your question?
Yes. Yeah. Thank you.
Okay.
Thank you very much.
I'm just gonna keep going, but thanks for your question. And it brings a really good point. So again, people have thought about this and have tried to sort of separate these two things. And they have looked into, for example, how energetic the gamma ray is. As I mentioned before, it's really hard to find the optical counterpart. So you will just have gamma rays. And what can you do with these gamma rays? Okay, you can get the how much energy what was the energy peak, how bright it was. We call that affluence. But generally, you're trying to separate these two things. So I'm here plotting in color from cyan to magenta the probability of being part of the short GRB population. So here are the short GRB population, and here are the long GRB ones. But you have this sort of a gray area here in which you don't really know for sure if it's a short GRB or long GRB. If you find the optical counterpart, you can probably get the redshift. So with the redshift, you can calibrate for the energetics. And this is the energy in the rest frame compared to the energy that it puts into the, sorry, the energy in the rest frame versus the peak energy. And you see here that long GRBs are sort of like well localized in this, we call it a Ahumada relationship because a guy named Ahumada sort of was the first one saying this. But you have long GRBs here, and then you have short GRBs out of this location basically. And our GRB 2008-26A was on top of this long GRB site. So when we discovered it, it was like, okay, it's a very short GRB, it lasted less than a second, but it also falls into the long GRB energetics. So we needed to investigate further. For that, you can do a bunch of stuff, and that probably goes also, it's related to what Sovam was asking. You can look at the afterglow. Afterglow properties will tell you how energetic it was, how much energy it was put into the system. The host galaxy will also give you some insight. You will expect collapsers to come from younger population and neutron star mergers coming from older populations. But eventually you will need to get the optical counterpart observed and studied. And in this case, we went for a supernova hand, and we actually found it. So that allows us to say that there is evidence that supports this sort of collapsar scenario versus the merger. So when you model the afterglow, you use what Peter was showing you, Bayesian inference, and you can get values for these properties. So an afterglow is very well modeled by how much energy is put into the environment and what's the density around the environment. So I'm just showing the kinetic isotropic energy and the density. For short GRBs compared to long GRBs, this is density. Long GRBs happen in denser environments. As I mentioned before, you would expect this sort of like material surrounding this long GRB because of this massive star. But then for short GRBs, you will expect a less dense environment. I put here on magenta the measurements that we get from our modeling. So it's consistent with being a short GRB. And when I say short GRB, I mean a merger origin. And then long GRBs, it was way too like less dense than we would expect. Energetically, you would expect a long GRB to be in the range of like 10 to the 50 to 10 to the 54. But for short GRBs, it's the range of energy is less. So you would expect it to be less energetic. And for our modeling, it was basically sort of like outside the distribution of short GRB, but it was in the center of the long GRB. So it's really hard to tell from the modeling of the afterglow, which is what people have done in the past, saying, okay, this is a way too energetic burst for it to be a merger. Let's associate it with a collapsar. So from just the afterglow modeling, it's really hard to say. It's not conclusive. So we want to study the host. So to study the host, you would get a spectrum of it. With the spectrum, you would get lines. These lines will tell you the redshift. So with the redshift, you can calculate the distance, and with the distance, you get an offset from the center of the galaxy. You would expect mergers to have evolved and have more time to evolve because you need to generate 2 neutron stars. And they go through supernovae, so we call it a supernova kick that will push them outside of the galaxy. So you would expect the offset to be greater than for massive stars that are usually closer to the center of the galaxy. So this is a cumulative distribution for long GRBs. So you see that they are basically closer in this and closer to the center of the galaxy, while short GRBs tend to be farther away. Our burst, the distance, it's consistent with both of them. It's not conclusive. From the same sort of spectrum and measurements of the galaxy, you can get the mass of the galaxy, you can get the age and stuff like that. And there's another compilation for long GRBs and short GRBs. Short GRBs tend to be in more massive galaxies here, 10 to the 9 to 10 to the 12 solar masses, while long GRBs tend to be in less massive galaxies. But our GRB here was in the middle, so it's again not conclusive. So that's another thing that you can look into. You can look into the host galaxy, but in our case, it was just not conclusive.
Hello, I have a question actually. So, is it okay to ask right now?
Yeah, sure. I mean,
Yeah. Can you go back to the previous slide? So why do we have a speculation as to why short GRBs are farther away and long GRBs are like nearer to the?
Yeah. So again, you require thinking that short GRBs come from mergers, right? A merger will require either a black hole or a neutron star. And to create a neutron star or a black hole, you have to go through the entire life of the star. And when it sort of like goes through a supernova, it will kick the it will give energy to the star to just keep going farther and farther away from the galaxy. So over this billion 10, I can't remember, 10 billion years, I think, of evolution, you will allow the star to go out of the nuclei of the center of the star. While for long GRBs, they tend to be younger stars. They're just like giant younger stars. So they are basically in the star forming regions of the galaxy, would tend to be closer to the.
Yeah, got it. I also have one more question that I'll ask at the end. I don't want to interrupt the flow.
Okay. So we went and looked for the supernova. So we got time at the Gemini Observatory, which is a much larger mirror. We got an image in September 23rd, and which is 28 days after. We were sort of like convinced at that point that we didn't see any sort of like kilonova behavior. So let's wait a little bit to get the supernova rise. And then we got a reference image 45 days after. And then when you subtract these two, which is also a very complicated art, you see here that there's a residual. And you can put this in context. So you have here the light curves. Here the circles are the data points that we have collected, and then you have on shaded regions the afterglow models. And you see that if you go this is days. So if you go into this history, you see that for IBAN, which is the yellow area, you would expect something much fainter than what we have observed. So we observed something that was way above what we have predicted. And we can actually calculate how far it is in terms of the probability distribution. So you can take sort of like a slice here and look for the probability density. So here's the afterglow. So this sort of like yellow region here, it's this here. And here you have the detection, which is, if you take the sigma here, it's around 4 sigma away from the detection. And we did it again, we modeled it again, but we added a supernova component. So we added something like this that rises up, whoopsie, that rises up and then goes down. And that fitted much better the data point that we had. So with that excess in the I-band, we were able to say that this was a collapsar, and that made it the shortest collapsar that we have ever found, lasting for 0.6 seconds. So what happened is basically that you have this massive star that the jet barely made it through the envelope, and we were able to observe that. And this is what we have done. And this is like from the beginning to the end, from tiling the regions to observing the supernova, how we have studied this object, that now we're trying to do the same for gravitational waves. This is the picture that we have had in the past, and this has been addressed just like in the previous question. So you have short GRBs that were observed with gravitational waves that were observed with a kilonova that everything links to a compact binary merger, because that's what the gravitational wave says. So everything here, like before like 2020, this was the picture, and it was separated from long GRBs that created supernovae and come from collapsing massive stars. So they're like these two different pictures, and they were very conclusive and separated. But now the 2008-26A, it's a short GRB, so it lasted for less than 2 seconds, but it created a supernova. So now it's linking this sort of situation here of short GRBs with collapsing massive stars. And there are now 2 different GRBs that happened, one in 2021 and one in 2023, a couple months ago actually, that link a long GRB, a very long-lasting GRB, 30 seconds one, and the other one 60 seconds, with an infrared axis that looks like a kilonova. So they took this optical counterpart, infrared counterpart, and fit it with kilonova models, and it apparently fits perfectly. So the question now is, now that we're facing 04, is, are we expecting also gravitational waves sort of coming with long GRBs? So now we went from something that was very clean to something that is like absolutely a mess, and it's super complicated. But since everything is connected, and what can we do? Like, how are we going to find the merger? So before we all panic, I guess we just have to take a break and breathe. And I'm just going to tell you what happened during 03. 03 was the 3rd observing run of LIGO. During the first observing run, they discovered the first binary black hole merger. During the second observing run, they discovered 17017. So everybody was super excited about the 3rd observing run. We took ZTF and triggered into 13 different events, sorry. This is one of them. This is one of the neutron star black hole mergers that is summarized in Shreyas and Michael's paper. And basically, we did a very similar situation to what we did with short GRBs. We tile the region, we observe candidates, and then we follow up the candidates. And the summary is here. We have more than 120 candidates. We did a very thorough analysis, but we didn't really find anything that was compelling. And I'm going to now talk a little bit about the details. So ZTF, the strategy of ZTF, it was at the time in a twofold situation. We either triggered, we took the telescope and point towards the fields that were that had a higher probability for to have the gravitational wave. The cons of it, it's that it's interruptive, it disrupts the survey, but it also allows us to go deeper because we can increase the observing time. Or we can just let CTF observe because it will observe anyways. So what we call serendipitous coverage is what happens just because. So here you have, sometimes the localization will be only 23 degrees, which is just one pointing of CTF. And that was perfect because we just go point once and that's it. But sometimes you have, I don't know, 7,000 square degrees, which is really impossible for us to just tile the region. So we just let CTF to do the job, and then it uses the nominal exposure. So again, it's well localized in terms of area. We can do like a targeted search, but when it's and this is what's called, it's purple. The purple sort of situation was a targeted event. Well, if it's covering half the sky, we might as well just let CTF do it. So this is the serendipitous coverage of one of the events. So this is 24,000 square degrees versus 2 square degrees. Same idea, we get candidates, we look for fast fading. This one, for example, was a fast fading. This actually is an afterglow. People are working on getting some information about this one. We got a beautiful spectrum, but it was very far. It's like redshift 1.2, I think. What has happened now, what has evolved between 04 and 03 and 04 is that now CTF is purposely targeting some of the maps. So nominally, CTF will cover the most of the night sky with this 30-second exposure. But what we have done now, it's that we went for a random coverage to a more dedicated coverage. So we can now reweight the coverage of CTF. So instead of having something that is random and is looking for something that is like, not gonna have any sort of probability, we can ask the schedule to concentrate its observations into these areas. So we have now the target of opportunity that allows us to go deeper, but we can optimize the serendipitous coverage. I'm just going to show you now some utils, some things that are, I think, found useful for gravitational wave searches. So this is GraceDB. In GraceDB, you have access to a lot of information of gravitational wave and electromagnetic follow-up. Basically, it's a Wikipedia for gravitational waves. It has everything that you probably will need in terms of definitions and what you're looking for. So if you see something that you don't understand from a gravitational wave alert, there's like basically a glossary, and you can find everything, it's even like the definition of GRB. So ideally, GraceDB will be one of your friends. So for you can see how what's the status of the interferometers, but it also allows you to go to the events. So there are two types of events, events and super events, but we're basically looking into all the detections that LIGO has seen. So I'm here just looking for one of the ones that we actually triggered. And here's like, I'll talk about this later, but then you have the map, and then you have the 3D distribution of the map. You have information about the properties of the events. Does it have a neutron star? Does it have a remnant? Does it involve, what does it involve? In this case, it's 44% neutron star, 20% binary neutron star. So GraceDB will be a good friend. And the other good friend is GCN. I'm not sure if you guys have been introduced. These are just basics of multi-messenger astronomy. This is the general coordinate network. It originally was intended for GRBs, but now it receives neutrino alerts and also gravitational wave alerts. You can go to this web page, create a user, and start receiving alerts. And this is just like a note. It's just like Tomas will, it's telling the community, hey, we observed something. So this is a circular from gravitational wave event that happened in May 29. So you have, it was just one observatory event. You have the pipelines that we're observing, and then you have the FAR, which is the false alarm rate. You have more properties like what it's actually been found. Does it have an S? Does it have remnant? Has the information about the localization maps, and how wide is the localization, and how far it is. So there are a bunch of properties that you might want to get acquaintance with. One of them is the false alarm rate, is how likely it is to be an actual alert. So the higher the false alarm rate, the worse in this case. So like we want a false alarm rate that is like very, very minimal. And then you have properties from the pipelines that tells you whether it has a neutron star or a remnant. So in this case, for example, I'm just plotting the probability of having of being a binary neutron star versus the false alarm rate. So we want something that is very a false alarm rate that is very short, small. So this is the line that marks 1 per year. This is the line that marks 1 per month. So there's only one event that has had a high binary neutron star probability and a low false alarm rate so far. Localization maps, you've already seen this, but I just wanted to mention that in this case, it's they observed something. They can't really tell where it was, but it has a sort of a 3D aspect that is what you will probably be playing on your notebook. So just think of it as if you take the probability and you're looking at it from different sides. So remember that this is the localization, right? This is the mean, the average distance. So it's centered in 217 megaparsecs, and it has some wings. But if you look it from the top, or if you're looking from the sides, it has a different shape. So the volumetrically, it's also interesting how LIGO will give you insights on what is the volume that it's involving this event. And then you can actually go and look for the galaxies that are in this volume and not just in the background, because you have now distance information. And one of the ZTF perks is that, so it's how big it is. So this is just one of the quadrants of the CCD. So ZTF has 16 CCDs, and each one of them has 4 quadrants. And this is one of them. I'm just going to put it larger. And this is just one. You can imagine how many transients you can find. And this is a 30-second exposure. So you can go deeper and go with a larger amount of exposure time, right? So this is how it looks with 180 seconds. So you start saturating stars, and it looks much. So things that were there's nothing here, but now you see stuff, because you're looking for sort of like very faint events, and this is just one ZTF field. So this is the amount of things that you can find in just one quadrant of the ZTF fields. That is just one of these squares. So when you look into this, it's like, oh, it's not that much. Well, like 15 fields, but each one of these has a tremendous amount of transients. And the idea is, how are you going to prioritize this? So in order to optimize this, you need to have a way to express the sky first into sort of like a computer a way to understand it. So they have created this pixelation. It's called HillPix. that it's depending on the level that you're going, you can sort of like tessellate the sky in different pixels. So each of these pixels will have a probability associated with it. And then you can say, okay, I'm going to observe this sort of portion of the sky first, and then I'm going to look the other one. But also, you need to take into consideration that we're limited by the night, right? So this is just to show you the observability. This is Pasadena during the day, and you see how the sun moves. I'm putting here the constellation, so the sun is in Cancer, but eventually, as you go into the night, this part sets, and you cannot really observe it. And actually, the planets are very close to the horizon. And if something, for example, if one of these regions happens to be closer to, I don't know, Cancer, you can only observe it during the beginning of the night. So you have to sort of like have that into consideration, but also the telescope cannot really look much into the horizon because you'll not see anything. That's what we call ERMAs. You have a limit. So actually you can only see sort of like this sphere over here. So there is this very useful package called WebMap. Actually, Michael is one of is the creator of WebMap, and it's what we use to optimize our observations, and this is how basically we prepare for this observation. And to end, I'm just showing you from top to bottom, I guess. How do we observe? So I'm not sure if you're familiar with Fritz, but Fritz allows you to get GCNs. In this case, I'm just filtering for gravitational waves. This is a gravitational wave map. This is the 90% credible region. You can go into the LVC, to the GraceDB page. This is a well-localized event, and it has a binary neutron star merger. It's a mock event. It's not a real event. So we were practicing into these things. Each of these squares is one of the ZTF fields. So you can select how many fields you want to observe. You can unselect fields. And you can make a plan. You can make an actual observing plan. For that, you can select different filters. You can select different dates. You can select different exposure times. And eventually, everything is now automated. You can just generate a plan, and then you have all the plans that have been generated, and it takes a couple seconds. And then you have, okay, this is the plan that ZTF gives me. So in this case, we can only observe a portion of the sky. Maybe if we only observe with 240 seconds instead of 300, we can see more. So then there you go. So it's loading the plan, and eventually here you have in this part the summary. So we can observe 30% of the probability, and in 300 seconds, and you can do 60 also almost if we do for 240. So ideally you would like send to queue, but you probably don't have the permissions if you have access to Fritz. But that's basically from top to bottom. You have to get the map, get the observing plan, and observe, and then you get the candidates. That's what you guys did yesterday. So with that, I guess I'm just gonna thank you and wish you a happy hunting, and just take questions.
All right, I think he can hear us. Okay. All right, questions for Tomas? Got one in the, yeah, come up here. Yeah, great.
Hi, Tomas. I was wondering if you could talk about the process behind determining host probabilities for GRB sources. And is it usually the case that these sources are localized in low dense environments?
So you're asking me about the probabilities of how to, you're talking about this one, So how
Right.
to determine what is the so it was very simple, honestly. It's a very simple approach. You plot all the bursts. You need to first get the duration of the burst and then get the peak magnitude, the peak energy, and then you put them in the plot, and then you just put 2D Gaussians, and that's it. You just measure how far from the peak of your Gaussian is, and that's your probability.
Okay, do you mind explaining that one more time? So I think I'm asking about.
So you have these two. Think of it as this. So if you want to know the probability of one event to be part of this Gaussian, you just take the distance to the mean, right? What's the sigma that corresponds to your measurement? So if your sigma is like, I don't know, it's 5 sigma, that means that it's outside of your distribution. So in this case, this is just a 1D example, and you can have a 2D distribution because you're doing 2 dimensions in this case. So you basically feed a Gaussian to this population and a Gaussian to this population, and you calculate what is the level of credibility that you are in for a given GRB. So in this case, this GRB, it's not 100%, a short GRB in the sense that it's not in the center of the distribution. It's in the outskirts of the distribution. So I think it was 70% a short GRB.
Okay, thank you.
Cool. And I guess you had another question.
No, you ended up answering it.
Okay, cool.
Any other questions for Tomas?
Yeah, I wanted to ask one. I told you I would do it at the end. So,
Sure.
Yeah. So, I think there was one plot where we had the theta j equal to 0.1. So, somewhere
So, what did you say? The plot that had what?
the angular resolution was set to a particular I think a 0.1 value, and then you were plotting. So it was earlier in the lecture.
0.1.
Yeah. The plot where we did, this plot. So why do we keep the angular resolution so low? Is it necessary to keep the angular resolution low? Are we detecting it from the polar region or the?
Yeah. So basically, what happens with a GRB is that the emission is very collimated. So you wouldn't detect the gamma ray radiation unless you are within the barrel of the jet. So within, and for people that were not we're a little bit lost, this angle, it's basically this aperture here. So 0.1, it's a very small number, but usually you need to be within this sort of barrel. If you're looking from here, you're not going to see anything because the radiation was jetted towards another direction. So there are a few other models that have a more complex description of the jet. So sometimes they will describe it as a Gaussian jet, which means that there is some radiation that goes into the other, so like outside of the jet. But it is much easier to, and the ones that we have observed actually are more of like a top hat thing, that you have nothing and then you have something and then you have nothing again.
Yeah, that's what I was wondering. Thank you so much for clearing this out, because I was thinking that if we are looking at it from the polar region, that would make sense, but from the outside, that would not make sense.
Yeah, so it really depends on where you're looking, and you might be able to see some radiation if you're outside, but not too much.
Okay, thank you.
Any other questions online? All right, if not, huge thank you, Tomas. That was really nice. Okay, so logistics. So like before, so we're going to take a break now. For in-person participants, we have our first outing today, which is encouraged but not required. So we're gonna, on the St. Paul campus, there's a museum, planetarium, that kind of thing, and we're gonna go see a show, that kind of stuff. So if you're interested, we'll meet at those doors at 1:30 and take the campus connector over. Otherwise, Andrew and I'm not sure if K Ryan, but we'll have TAs still here watching the stuff, you know, working with folks who want to work on the exercise as well. And on Zoom, we'll, you know, reopen Zoom at 2 per usual. So yeah, otherwise food should be here in the next couple of minutes, and otherwise we'll meet at those doors in looks like 1 hour and 20, something like that. All right, thanks everyone. The meeting.